So let's look at this question. We have a circuit, and it says for the circuit shown below, calculate the A, effective resistance of the parallel group, B, total circuit resistance, C, total current I, D, PD V1 across the parallel group, PD, E, PD V2 across the 3.5 ohm resistor, and F, current I1 and I3. So this should be I3, right? Actually, I2. So current I1, I2. Good. Now let's examine the circuit. So we have a battery of EMF 16 volts, which is driving a current I. So we know that basically this is a conventional current I, which always flow from the more positive terminal of the battery around the circuit to the negative terminal of the battery. So if you remember, conventional current basically flows in the opposite direction to which electrons would flow. So the total current I flows around and it gets to this junction. It gets to this junction and it sees two paths. It sees a path to a 6 ohm resistor and a path to an 18 ohm resistor, and it splits because the current must flow, a part of the current must flow in each path. So I1 flows towards the 18 ohm resistor, I2 flows towards the 6 ohm resistor. Now these two currents flow to their respective resistors, but they will recombine at this junction, and the total current I will now also flow through the 3.5 ohm resistor. So therefore these two resistors, the 6 ohm and the 18 ohm, are connected in parallel, and that combination is in series with the 3.5 ohm resistor. So when the question refers to the parallel branch, they're talking about this comprising the 6 ohm and the 18 ohm resistor. Right? So let's look at that part of the question. So part A. Now we know that basically there's a formula to calculate the effective resistance of resistors connected in parallel. And of course, if there are two resistors, we have 1 over RT equals 1 over R1 plus 1 over R2. But of course, if it's just two resistors, then the total effective resistance is simply their product divided by their sum. And since we already have this equation, we'll just proceed to show how we come about with that formula. So treating these as two fractions, we can basically draw a line and form the common denominator is obtained by multiplying the two denominators, right? So R1, R2, right? So if it was say a half and a 3, we'd say 2, 3, 6. The LCM would be 6. And in this case, of course, the common denominator would be R1, R2. So say R1 into R1, R2 goes R2. R2 times 1, that gives us R2 plus R2 into R1, R2 goes R1. R1 times 1, that is R1. So this is equal to that. 1 over RT is equivalent to that. And if we simply flip both sides, we get that RT is equal to R1, R2 divided by R1 plus R2. So basically, if we ever have two resistors connected in parallel and we want to find the total effective resistance, we don't need to go through these baby steps of writing down the fractions, finding common denominators and so on. We simply find their product and we divide that by their sum. So in this particular case, the two resistors in the parallel branch are 6 ohms and 18 ohms. And so let's call that effective resistance RP. So it will be RP is equal to 6 times 18 divided by 6 plus 18. So this gives us 6 10 60, 6 8 48. So this is 108 divided by 6 plus 18, 24. So 24 will go into 96 4 times. That leaves 12. So this gives us 4.5 ohms. So therefore, the effective resistance of the parallel branch is 4.5 ohms, right? So essentially, these two resistors connected in parallel are equivalent to a single 4.5 ohm resistor, right? Now let's look at part B, the total circuit resistance. So essentially, having found equivalent resistance of these two in parallel, essentially this is equivalent to a single 4.5 ohm resistor right? And so therefore, that combination was now in series with the 3.5 ohm. So therefore, the total circuit resistance, let's call that RT. So RT would be equal to 4.5 ohms plus 3.5 ohms, which gives us 8 ohms. So the total effective resistance in this circuit is 8 ohms, right? Now, let's look at part C. Now, having found the total resistances, of course, we can then proceed to finding the total current I, right? So what we have is a total resistance RT, which is 8 ohms, and of course, we have the total PD across this combination, which is the battery's EMF, 16 volts. So using Ohm's law in the form V is equal to IR. So for part C, we know I, the total current, is equal to V over the total effective resistance RT, and this gives us 16 volts divided by 8 ohms, which of course is equal to 2 amperes. So the total current I flowing is equal to 2 amperes. Good? Now let's look at part D. The PD V1 across a parallel group. Now, for the parallel group, we know that the total effective resistance is 4.5 ohms. So we say RP is equal to 4.5 ohms. And for this parallel group, the total current I flows through the entire combination, right? So what we're seeing is the two individual currents I1 and I2. But the total current flowing through this combination of resistors is the total current I, which of course is 2 amperes. So I equals 2 amperes, and the PD V1 would be equal to IRP, which would be equal to 2 times 4.5, which of course is equal to 9 volts. And so therefore the PD across a parallel branch is equal to 9 volts. Part E. Now, having calculated the PD across a parallel branch, we can calculate the PD across the 3.5 ohm resistor in two ways. The first way is to basically multiply the current flowing through it by its own resistance. So we can say V is equal to, so let's call it V2. So V2 is equal to IR, and that will give us 2 amperes times 3.5 ohms, which of course gives us 7 volts. So that was one way of calculating the PdV2. However, since you know that this combination is in series with the 3.5 ohm resistor, it means that their total PDs must be equal to the sum of their individual PDs rather, must be equal to the total PD across them, which of course is equal to the battery's EMF or the battery voltage, right? So therefore the PD V1 plus V2 is equal to 16 volts since they're connected in series. And we could have actually found V2 via that method, right? But since we already found V2, let's proceed to part F. So F wants us to calculate the currents I1 and I2. Now I2 flows to the 6 ohm resistor and I1 flows to the 18 ohm resistor. So from our knowledge of resistance, we know that basically resistance is a measure of the opposition to the flow of electric charge or the flow of electric current. So what this basically means is that we expect the smaller portion of the current to flow to the larger resistor and the larger portion of the current to flow to the smaller resistor. Now, since we already found the PD V1 across the parallel branch, and we know that whenever components are connected in parallel, the PD across them is the same. So therefore, the PD across the 6 ohm and the 18 ohm will be the same at 9 volts, and therefore we can actually calculate the individual currents flowing through each, right? So for the parallel branch, of course, you know that V1 is equal to 9 volts. So therefore, for the 6 ohm resistor, we can say I, that is I2, is equal to 9 volts divided by 6 ohms, which is equal to 1.5 amperes, right? And for the 18 ohm resistor, we can say I1 is equal to 9 volts divided by 18 ohms, which gives us 0.5 amperes, right? And as expected, the two currents add to give the total current I, which was found to be 2 amperes. So let's look at another question. We have the circuit and we're told for the circuit shown below, calculate the unknown currents. Now the first thing we must do is to determine basically how these resistors are connected, whether they're connected in series or whether they're connected in parallel. The next thing we must do basically is to find the total effective resistance of the entire circuit. So we need to find the total resistance or the total effective resistance for the entire combination, and then basically that will allow us to find the total current I and so on, right? So that is basically one approach. So let's look at this question. So first of all, let's look at the different branches. So we see that basically we have, let's say this is a 180 volt battery. Seems pretty large, but I mean, that's the information we're given in the question, right? So this battery is driving a current I. This junction, the current splits. A certain fraction I1 flows to the 60 ohm resistor. It continues and splits again. Second fraction flows to this branch, 40 ohm and the 50 ohm connected in series. And then of course, a third portion, I3, flows to the 10 ohm, 20 ohm and the 30 ohm connected in series. So these three resistors, the 10, 20 and the 30 ohm are connected in series. These two, 40 ohm, 50 ohm are also connected in series, and the three branches, however, are connected in parallel. So what we could basically do is to simplify these numbers and then redraw the circuit with a single resistor in each place. All right? So 10 plus 20 plus 30, that is 60. So essentially we have a single 60 ohm resistor, +40 plus 50, that is 90. So essentially in that branch we have a single 90 ohm resistor, and of course we have a 60 ohm resistor. So essentially those three resistors are connected in parallel, and across them we have a 180 volt battery. Driving a current I. This right here is I1, I2, I3. Right? So, one approach would be to find the total effective resistance of the entire combination and then use that with the PD to find the total current I. That would be one approach. But usually, in any question, there's usually more than one approach. And the other approach is to basically find the individual branch currents, I1, I2, I3, and then add them up to give the total current I. So the total current I, being driven by the battery, will be equal to the sum of these individual branch currents. Now, we already established that these resistors are connected in parallel. And essentially, of course, the 60 and 90 are equivalent to these three rather in series, these three in series. So basically, if we were to build a circuit with these values, it will have no different functionality from this one built with, for instance, a 10, a 20, and a 30 ohm, as opposed to a single 60 ohm resistor. Likewise, there would be no difference if we use a 40 ohm and a 50 ohm connected in series, as opposed to a single 90 ohm resistor, right? So again, because these are connected in parallel, the PD across each of them is the same and is equal to 180 volts. So we say the PD across each resistor is the same and is equal to 180 volts. Good? So therefore, for the 60 ohm resistor, we have I1 is equal to V over R. So that gives us 180 volts divided by 60 ohms, which gives us 3 amperes. For the 90 ohm resistor, we have I2 is equal to V over R again, so 180 volts divided by 90 ohms, and that gives us 2 amperes. And for I3, which is flowing through the second 60 ohm resistor, so this is 60 ohm at the top, of course, that is the same resistance, and the PD, of course, is the same. So therefore, I3 is equal to I1, which of course is equal to 3 amperes. So I3 is equal to 3 amperes, right? So basically, if we have the same resistance and the same PD across them, then naturally the current flow must be the same, right? And now that we found I1, I2, I3, the total current I is equal to I1 plus I2 plus I3, which gives us 3 amperes plus 2 amperes plus 3 amperes, which is equal to 8 amps. So therefore, the total current flowing in the circuit would be 8 amperes. Now, earlier we mentioned a different approach. So that basically we could have actually taken a different approach, which would have been to find the total effective resistance in the circuit, then use it to find the the total current I, and then use that to find the individual currents. But that is the least favorable of the two approaches, right? So the more straightforward thing to have done was to actually find the individual currents and then use them to find the total current I. In this question, we're also expected to find the unknown currents, right? Now let's examine the circuit. So in this circuit, we have a single 12 ohm resistor, and of course we have a 3 ohm resistor, 4 ohm resistor, 12 ohm resistor. Now, how exactly are these resistors connected? So the 3 ohm resistor and the 4 ohm resistor and the 12 ohm resistor are all connected in parallel, and that combination is connected in series with the 12 ohm resistor. So the battery of EMF 9 volts is driving a current I. The entire current flows through the 12 ohm resistor. At this junction, the current splits. A portion I1 flows to the 3 ohm resistor, I2 flows to the 4 ohm, I3 flows to the 12 ohm, and these 3 currents will recombine at this junction, and the entire current flows back to the battery. Right? So with this particular question, what we will do is we'll find the total effective resistance of the parallel branch. We will then use that to find the total resistance in the circuit. We can find the total current I, and then that will allow us to find the PD across the parallel branch, and then that will allow us further to find the currents I1, I2, I3. Right? So let's examine the parallel branch. And we'll call its effective resistance RP. And therefore, we have 1 over RP is equal to 1 over 3 plus 1 over 4 plus 1 over 12. Right? So we have 3 resistors connected in parallel, and therefore 1 over RP is equal to 1 over 3 plus 1 over 4 plus 1 over 12. Just to work this out, well, all right, let's do the simpler way. We have the LCM of 3, 4, and 12 is 12. 3 into 12 goes 4. 4 times 1 is 4. 4 into 12 goes 3. 3 times 1 is 3. 12 into itself goes 1. 1 times 1 is 1. And so we have 1 over Rp is equal to 4 plus 3, 7, plus 1, 8, is 8 over 12. And therefore, this means that Rp is equal to 12 over 8, which is equal to 1.5 ohms. So the total effective resistance of the parallel branch is equal to 1.5 ohms. So essentially, all of this is equivalent to 1.5 ohm. So all of this, as I said, it could be replaced with a single resistor of resistance 1.5 ohms if possible, right? Now let's proceed now to find the total resistance in the circuit. So with this effective resistance calculated, the effective circuit essentially now looks like this. So it essentially looks like this. So 12 ohms, 1.5 ohms, and across that we have a 9-volt battery, right? So essentially this circuit is functionally equivalent to this one, right? Now the total resistance RT would be equal to the sum of these two, because of course they are connected in series. So remember, these three are connected in parallel and the entire combination is connected in series with the 12 ohm resistor. So we have 1.5 ohms plus 12 ohms, that gives us 13.5 ohms, right? So now that we found the total current, total resistance rather RT, we can now proceed to finding the total current I. So we can say that I is equal to V over RT, where V of course is the battery voltage or the battery EMF, and so this gives us 9 volts divided by 13.5 ohms. And what does that give us? Let me see. Where's my calculator? So that gives us 2/3 of an ampere, or 0.67 amperes. 0.67 amperes, right? So the total current flowing I is equal to 0.67 amperes, or approximately 2/3. So having done that now, what we'll then do is to find the PD across the 12 ohm resistor, and that will allow us to find the PD across the parallel branch, and we'll then find the individual currents I1, I2, and I3. So therefore, for the 12 ohm resistor, the PD, let's call that V1, right? And we'll call the PD across the parallel branch V2, right? So V1 is equal to I, which is 0.67 amperes, times 12, because this is exactly equal to 2/3. 2/3 of 12, then that gives us 8 volts. So V1, the PD across the 12 ohm resistor, is equal to 8 volts. Now because this 12 ohm resistor and this branch are connected in series, then their total PD must be equal to the PD across the battery. So if this V1 is equal to 8 volts and this is 9, then it therefore means that V2 is equal to 1 volt. So V2 is equal to 1 volt, which of course is going to give us pretty small currents for each of these, right? So having found V2, we can then proceed to finding the individual currents, right? So I1 would be equal to 1 volt over 3 ohms, which of course we could leave it as a third, or we could write it as 0.33 amperes. Then I2 is equal to 1 over 4, well, or 0.25 amperes. And then lastly, I3 is equal to 1 over 12, 1/12 of an ampere, and that should be approximately 0.42. No, how much you're gonna get? No, sorry. So 0.09, approximately 0.09 amperes, somewhere around there. 0.09 amperes, right? Because of course we know that all three must basically add to give 0.67, which of course we rounded, right? So in this question, we basically found the total effective resistance of the parallel branch. We then found the total resistance in the circuit, used it to find the total current flowing, then the PD across the single 12 ohm resistor, from which we found the PD across the parallel branch, and that allowed us to find the individual currents I1, I2, and I3.